Welcome to another physics class. During our last lesson, we concluded the topic projectile motion. So today, we are going to simple harmonic motion. And when you say simple harmonic motion, it simply means the motion of a particle whose acceleration is directed toward a fixed point or toward an equilibrium position. And the acceleration is directly proportional to the displacement from the equilibrium position. That's the simple definition of simple harmonic motion. But when you say harmonic motion, it's motion that repeats itself in an equal interval of time. That is, when you say harmonic motion, means motion that repeats itself in an equal interval of time. So to write simple harmonic motion simply means simple harmonic motion means motion of a particle whose acceleration is directed toward a fixed point. And the acceleration is directly proportional to the displacement from that fixed point or an equilibrium position. That is, the motion of particle whose acceleration is directed toward a fixed point, and the acceleration is directly proportional to its displacement from that fixed point or an equilibrium position. Now, when you say harmonic motion, that's motion that repeats itself in an equal, regular interval of time. That is, the motion will repeat itself in an equal interval of time. That is why we call it harmonic motion. Now, examples of simple harmonic motion. Examples of simple harmonic motion. 1. The first example is a swinging suspended pendulum bulb. That is a swinging suspended pendulum bulb. That is, it will have an equilibrium position like this. Then, when you now displace it with a little angle, then it will now move to and fro. From the equilibrium position, it will move to and fro like this, to and fro like this. That's what made by simple harmonic motion. You can now say that the motion will repeat itself with equal regular time interval. So the to and fro movement of a simple suspended pendulum now is a typical example of simple harmonic motion. Another example, example 2. Vibration, vibration of a prong tuning fork. Vibration of a prong tuning fork. And when you take a tuning fork, you hit it on a hard subject, it will vibrate. That vibration also is a typical example of simple harmonic motion. This a tuning fork is something like this with two arms. So when you hit it with hard material, it will vibrate. So the vibration is also a typical example of simple harmonic motion. Number 3, vibration of a plug guitar. When you plug a guitar, then it will vibrate. The vibration is also a typical example of simple harmonic motion. Number 4, vertical oscillation of a loaded test tube placed on water. Vertical oscillation of a loaded test tube placed on water. That is, when you have a bowl of water like this water, you now load a test tube, you displace it. Definitely, the test tube will be oscillating up and down, up and down. That is a typical example of simple harmonic motion. That is the up and down oscillation of a loaded test tube placed on water is another example. With number 5, the beating of heart. The beating of heart. That is the heartbeat. When you place your hand in your chest like this, the heart must be 72 beats per minute. So the beating of heart is another example of simple harmonic motion. Number 6, the pulse of blood pressure flowing in the vein. Number 7, motion of a ball or marble placed on a concave surface. Placed on a concave, so that let's say this is a concave surface. When you place ball on it, the ball will roll down, and to go back, this is the equilibrium position. So it will roll down, up, up, up like this. So the motion will be like this. It will roll down, roll up, and go back, settled in the equilibrium position like this. So this is a typical examples of simple harmonic. Number 8, the vibration of electron in a radiating and receiving antenna. Vibration of electrons in a radiating and receiving antenna. That is, when you check an antenna, the electron will be radiating around it. So that also is a typical examples of simple harmonic motion. Number 9, vibration of atoms of solid about their equilibrium position. That is, when you hit a solid material, the atom will vibrate and give out sound. But when you hit them, the atom will vibrate and give out sound. So the vibration also is a typical examples of simple harmonic motion. Number 10, the to and fro motion of a wall clock. The to and fro motion of a, let me call it pendulum wall clock. Pendulum wall clock. That is the toe, like that suspended simple pendulum. A pendulum wall also will perform simple harmonic motion. The to and fro is also a typical examples of simple harmonic motion. Let me add more. Number 11, vibration of a beating talking drum. These are the possible examples of simple harmonic motion. The next is term used in simple harmonic motion, SHM. The first time we are going to look at is cycle, or you can call it vibration, or you can call it oscillation, or you can call it revolution. So call it any one of the 4 names. So when you say cycle, is a complete oscillation of a vibrating body. Complete oscillation of a vibrating body. And one complete oscillation, as I said, under circular motion is equivalent to 360 degree or 2 pi rad. That's one complete oscillation. 2. Period. Period. The symbol for period is capital T. And period is time taken. Is time taken to complete one cycle. The time taken to complete one cycle is what we mean by period. Or you can also say period in symbol T is equal to 1 over F. That's the formula for period. That is 1 over F. And the next we are going to is frequency. That's number 3, frequency. And when you say frequency, this one is the number of oscillation, per second. Number of oscillation per second. That is number of oscillation per second is what meant by frequency. That is frequency will be equal to N over T, where N is what? Where N is equal to number of oscillation or number of cycle. T is equal to time taken. Now, from what we've seen on the board now, frequency also can now also be the unit of frequency under this one is per second. When you say number of oscillation over time taken, so the unit of frequency, the unit of frequency is per seconds per second, that is per seconds. Then you can still have the unit of frequency or hertz. Hertz. This one denoted by hertz. That's another unit of frequency. So frequency also can be, F also can be 1 over capital T. That is where per second come from, because the unit of period is seconds. So the unit, this one also can be period, can also be, according to this thing now, period also can be, since frequency is N over T, you can now say 1 over N over T, which one, this one will now give us T over N. So the formula for period also can be T over N, where T is what? Time taken. Is time taken. This one is small t. Now, when you say time taken, is time taken by a particle to complete any cycle. To complete any cycle. This may be any cycle. It may be half cycle or 1/4 cycle or 3/4 cycle, or talk of any cycle apart from one complete oscillation. That is, when a particle covers either less than or greater than a complete cycle, which is one revolution, then the time there is called time taken, which we use small letter t to represent. But when it is for complete oscillation, so that one is period, and is the time taken to complete one cycle or one oscillation. So that's for period. But small t will represent any time taken out to complete any cycle. Number 5, amplitude. Amplitude. When you say amplitude, amplitude is the maximum and minimum particle displacement of a vibrating body. That is maximum and minimum. That is, I said, particle, the minimum and maximum particle displacement of a vibrating body is what meant by amplitude. Now the fourth term now, let's use a profile to represent them. I mean, when you say oscillation, the circle diagram is something like this. So for a complete oscillation, it follows a sine curve. This is a complete oscillation. This is equilibrium position. So from here to here, from here to here, this is a cycle or complete cycle. Complete cycle. When you talk in terms of time, from here to here, this period t, that is the time taken. But when you now talk in terms of time taken now, when you consider, let's say you take from here to this particular point, then you now talk about from here to here as small t. I want to take from here to here. Apart from this complete cycle, any other part you use small t to represent that is the time taken. Now, when you look at it, we say amplitude. Now, from here to here, this maximum amplitude. Maximum amplitude. From here to here, this minimum amplitude. That's why we define amplitude as the maximum and minimum vertical displacement. This is the vertical displacement, maximum. This is minimum because this is the equilibrium position. That is the point of center zero. So that's the equilibrium position. That is the point where the object will start oscillating. So this is for a complete cycle now. from here to here, a complete cycle. When you talk about period, the time taken to cover from here to here is period. If you take any section or any part, as I said, from here to here, it will be time taken. So that is the major term used under simple harmonic motion. If you look at this profile again, if you talk about frequency, that is the number of oscillations per second. So this is one oscillation, as I said, one cycle. S is displacement S of simple harmonic motion. But before we go to this one, let me quickly remind you what we have done under uniform circular motion. And that is why I said, for you to enjoy this lesson, please you need to go back and watch our video on uniform circular motion. Because part of what we did under uniform circular motion is we are going to apply them here. But let me recall from uniform circular motion. From uniform circular motion, one displacement by then we say x is equal to theta r. Don't forget, by then I use s as displacement. That is, s is equal to theta r. So also number 2, Roman figure 2, linear velocity v is equal to omega r. Roman figure 3, angular speed of velocity omega is equal to theta over t. Roman figure 4, angular acceleration, or you can call angular or radian, or centripetal acceleration A is equal to v square over r, or omega square over r, omega square r. That's another formula for centripetal angular acceleration. Figure 5, by then we talk about centripetal, or you call it centrifugal force. That is, Fc is equal to mv square over r, or you can say MAC, where this AC is centripetal acceleration, and omega square r. Now, where theta, where theta is equal to angular distance, or you call it angle turn through, angle turn through. What else is there? Our omega is angular speed or velocity. T, time taking. What else is there? R, radius of the circular path. All are what we discussed under uniform circular motion, which we still need to apply under this simple harmonic motion. We've seen under uniform circular motion, we've seen the relationship between linear velocity and angular speed or velocity by then. So if you want to enjoy it more, please try as much as possible to watch our video on uniform circular motion. We produce 2 videos on that, which we call it uniform circular motion A and B. Try to watch it and you join it to this simple harmonic motion. By the time you do that, you understand this topic better. Having remind all this one now, let's now go to displacement. Displacement S of simple harmonic motion. Now, to understand it better, I want to relate it with circular motion. When you have an object moving in circular paths like this, let's say this is the equilibrium line. The object starts from this point and move in a circular path. Let's call this point A and move in a circular path. This is the highest point. Let's call this A, B, C, D, E, F, G, and this place is and back to the equilibrium position. When the object is rotating round like this, and when you draw the vertical line, this is the vertical line as the object moves from equilibrium position A to B and from B to C. It means if you look at it, when you cut our R here will be from here to here or from here to here, or any circumference, any point on the circumference here is our R. But mind you, under this one, our R, we now change to A, which is equal to amplitude. As we said the other time, amplitude. And the amplitude, when you now relate this one to what we have under a complete cycle of simple harmonic motion, complete cycle, something like this, this is a complete cycle. Don't forget again, under uniform circular motion, let me remind you again, it said pi radian is equivalent to 180 degrees. Therefore, pi over 2 radian will be equal to 90 degrees. At the same time, when you have 2 pi radian, 2 pi radian. This one will be equivalent to 360 degrees. By the time an object starts its motion from here and move like this and move and come back, that's so the complete oscillation will be done. If that is the case now, from here to here now, here will be pi over 2, which is equivalent to 90 degrees. So this one will be point C now. From here to here, that is 2 pi, 2 pi. That's so that this point will be point E, which is equivalent to what? 180 degrees. By the time you got to display will be, that's 3 over 2 pi, that's 270 degrees. So this will be 3 over 2 pi rad. That is 270 degrees. And by the time the object come back to this equilibrium position, that will be 2 pi rad, and which is equivalent to 360 degrees. Then what are we talking about? We want to look at displacement of simple harmonic motion. When you now say displacement, you know displacement will be angle made with particle. That is this particular angle, theta. When you now consider it, displacement now, this place will be our x, or from here to the point of intersection, this will be x. So when you now consider this our angle now, this angle theta now, when you now look at it, you consider it from here. This one will be opposite, and this is the line of this one. This one will be opposite over hypotenuse. Our hypotenuse is from this place, the point of center of the circle. That's, let's call it OB. So from there now, our sine theta will be equal to opposite, that is our s, which is displacement, or if you label this place as NBN, then the hypotenuse over OB. Then that one will now give us x over OB. Then our s now, mind you, this our OB, as I said from the beginning, is the equivalent to our, which is our amplitude. So this one will now be, instead of using R now, because under this one we are talking about amplitude, not radius. So we are going to say over A, which is the from here to here, or from here to here, or from here to here, which is equivalent to the radius of the circle or the amplitude. So, or this is the amplitude. This is the amplitude, as I explained the other time. So we are going to have cross multiply. Now you are going to have our s now will be equal to A sine theta. What the s stood for, that's our displacement. It means our s now is equal to A sine theta. Therefore now, you can now say but our theta from here, our theta, look at our theta here. Our theta, if you cross multiply here, our theta will be omega t. From this Roman figure 3. So our theta here will be omega t. So our theta now will go equal to omega t. So our s now will now be equal to A sine omega t. So the displacement of simple harmonic motion now will now give us, you can now say, therefore, the displacement of simple harmonic motion S will be equal to A sine omega t. A sine omega t. Where A is what? Where A is what? Amplitude. amplitude, and this omega is angular speed or angular frequency. Angular speed, or you call it angular frequency. Then our T there is time taken. Time taken. Now, if you consider it from this angle, from this side, our theta will be angular distance or angle turn through. Angular distance. Angular distance. So it means the magnitude of the displacement of simple harmonic motion depends on the amplitude, that's number one, the angular frequency or angular speed, and the time taken. Now, the next thing is displacement time graph of simple harmonic motion. This is just the repetition of what we've shown here, just to elaborate it. When you say displacement time graph, it will follow a sine curve. So this is y, and this is time. So when you show it like this, for a complete oscillation, for one complete oscillation, it will be like this. Now from here to here, this is maximum amplitude. From here to here, this is minimum amplitude. So as I said the other time, this is a complete cycle. A complete cycle, that is from here to this point. This is one complete cycle, one cycle. And from here to here, again, this period, that is the capital T. So this one will show a displacement time graph of simple harmonic. Now, the next thing is velocity of simple harmonic motion. That is, as I explained, during circular motion, when an object is moving a circular path, an object moving a circular path, this is the equilibrium position, and let's say it's moved along this circular path like this, the velocity, as I said, during uniform circular motion, although the object will move with constant speed, but due to the fact that it will be changing in direction, so the velocity also will be changing. So it will be, let's pick this point at the point of, so we are going to have it like this. This is the direction of velocity at this particular point now. So as I said, the velocity of this particular object will be tangential to the radius of the circle. That is, it will cut the circle at a point which is perpendicular to the radius. That is, this angle now will be 90. So therefore now, the angle that made here will be theta. That's angle theta that make. So here is the tangential velocity, Vt. Then I explained by then that this tangential velocity, we have two components. One, we have the horizontal x-axis component, x-axis, or x component, which is Vs. At the same time, it will have y-axis or y component, which is Vy. But since for Vy now, this is Vy, this is Vs. Now, since now Vy is perpendicular to the radius, so Vy, according to the theory, will be equal to 0 because it's perpendicular to the direction of the radius of this circle. So from there now, we are now left with the Vs. Now to find this Vs now, the component, the Vs component now. So you now let's look at it together. This is angle theta. Take this line and this tangential velocity. This one will now give us this adjacent, this is hypotenuse. That will be cos theta. Cos theta will be equal to Vs over Vt. So from there now, we can now say Vs will be equal to Vt cos theta. Now note this formula. This is velocity component of simple harmonic motion. But our Vt, as I said the other time, is equal to omega r. At the same time, our theta, as I told you the other time, omega t. Now substitute omega r for Vt and omega t for this one. We are going to have our Vs will be equal to omega r, then cos omega t. Note the formula again. Now from Vs is equal to omega r cos omega t. This is the velocity component, that is, this is the velocity component of simple harmonic motion. That if V is equal to omega r cos omega t is the velocity component of simple harmonic motion. In any calculation, when you have to calculate the velocity component, then you use this formula. To show the velocity time graph of simple harmonic motion, from this formula now, you can now say that unlike that of displacement time graph, which follow sine curve, this one will follow cosine curve. This velocity, this is time in second, velocity in meter per second, and to follow the curve will look like this. So the curve will look like this. This is our time, this is velocity. Then, since this one will represent our amplitude, so this place will be omega r. This is another, at this particular point, this is another omega r. This is another point, omega r. That is how the velocity time graph will look like. That is the velocity time graph, that is velocity time graph follow a cosine curve. From displacement of simple harmonic motion, we have x is equal to a sine omega t. It means sine omega t will be equal to s over a. At the same time, from velocity component of SHM, we have, according to what is on the board, that is this equation, Vs equal to omega r sine omega t. So at the same time, sine omega t will be equal to Vs over omega r. Now, using the trig identity, we say that sine square omega t square plus cos square omega t is equal to 1. So we are going to have s over a into square plus v s over omega r all into square is equal to 1. Then, since we need velocity, make v this term the subject of the formula. So we are going to have v s over omega r all into square equal to 1 minus s square over a if that is the case, this one will now give us v. Don't forget our vs indicate the velocity that we are looking for. That will be over omega into square will be equal to 1 minus s square over a square. Now, from there now, we are going to have v v over omega. And don't forget, okay, let's continue. Square will be equal to a square. That will be when you divide this one also by 1, then the LCM will be a square. So a square divided by a square, that will be, I will give us a square minus s square. So from this one, remove this one will now give us v square omega square will be equal to a square minus s square over a square. So from this one now, multiply through by this one. So we are going to have v square s will be equal to omega r a square minus s square over a square. Now, don't forget that I said the other time that this our r, we borrowed that r from uniform circular motion, is equivalent to a. If that is the case, then we can now have this one, v square is equal to omega square a square into bracket a square minus s square over a square. So a square will cancel a square. If we agree together that r is equal to a, that is the amplitude. So a will cancel a. So we are going to have v will be equal to omega square into a squared minus s squared. So taking the square root of both sides, we are going to have v, that is now the velocity of the simple harmonic motion will equal to the square root will cancel each other. That will be square root of a squared minus s squared. This one will be the velocity of simple harmonic motion. That is, this is the velocity of simple harmonic motion. When you have to find the velocity of any object performing simple harmonic motion, this is the general formula for the velocity. But this one will take place. V will be maximum now. V, that is, the velocity will be maximum when s is equal to 0. The velocity will be maximum when s is equal to 0. That is, at the mid or central point, or the equilibrium, central point or equilibrium position. So the velocity will be maximum when s is equal to 0, or at the central point or equilibrium position of the particles. When velocity is maximum, we are going to have V maximum will be equal to omega root A squared, which is also V maximum will be equal to omega A. That is when the velocity will be maximum. Well, that's the value of the maximum velocity of simple harmonic motion. The velocity of SHM, that is simple harmonic motion, will be minimum where, when A is equal to x. And when A is equal to x, we are going to have the minimum velocity, which the value equal to 0. That is when A is equal to s. If A is 2 and s is 2, 2 minus 2 will give us a 0 multiplied by this one. So we are going to have the minimum velocity when s is equal to 0. And this one will occur at the extreme point of the motion. It will occur at the extreme point of the motion where we have the minimum of least velocity. The next is acceleration of simple harmonic motion. The first point we are going to note under this one, as the velocity is taking place on x-axis or x component, acceleration of simple harmonic motion also will be acceleration of SHL will be on x-axis also, or x component. 2. The acceleration is directly proportional to the displacement x. Acceleration is directly directly proportional to displacement S, that is A is directly proportional to X. Number 3 point, the acceleration is directed towards an equilibrium position. Is directed toward an equilibrium position. 4. The acceleration is in opposite direction to displacement S. Therefore, it takes negative sign. That is, A will be equal to minus omega square A. That's the magnitude of acceleration of simple harmonic motion. That is, A is equal to minus omega square A. Why is it minus? Because according to the number 3 and number 4 point, is directed toward a fixed point. It is opposite in direction to displacement. Where S is displacement, and S is equal to A sine theta. Therefore, our A now is equal to minus omega square A sine theta. And don't forget again, our theta is equal to omega t. So our A now will be equal to minus omega square A sine omega t. That is the acceleration of simple harmonic motion. Maximum acceleration, that is, A will be maximum. A will be maximum when the displacement is maximum, and rather when velocity is equal to 0. And this one will occur at the extreme point of the motion. At the extreme point of the motion, when S is equal to A, that is when the displacement is equal to amplitude. Don't forget our capital A is amplitude. So when S is equal to A, we are going to have the maximum acceleration, and the value of the maximum acceleration, as I wrote here, will be A maximum will be equal to minus A square, either A or S. Just take anyone. When S is equal to A, we are going to have maximum acceleration at the extreme point, or when velocity is equal to 0, or when we have the maximum displacement. This will be the last aspect for today, that is the acceleration time graph of SHN. when you have the acceleration time graph from this one now, it's just the inverse of displacement time graph. Is what we may call what meant by acceleration time graph of SHN. Unlike that of displacement time graph, which follow a sine curve, this one will follow it like this, just the inverse of that the acceleration, the displacement time graph or simple harmonic motion. This is A in meter per second square, and this is time in second. Here is the omega square S or A. This is omega square S or A. This is omega square S or A, and omega square S or A. So the acceleration time graph will look like this, just the inverted displacement time graph. It follow an inverted displacement time graph of SHM. Please note, we are going to stop for today. In our next video, all the formula we derive under this lesson now, we are going to apply them in solving some questions under simple harmonic motion, and that will be the general formula for simple harmonic motion. We are going to use them to solve some problems. So, as I said earlier, if you have not watched our video on uniform circular motion, please try as much as possible to watch it before you come to this simple harmonic motion, so that at the end of the day, you can understand the two topics together. And if you are just with us today, that is, you've not joined us before, you are just joining today, please try to like, share, and subscribe. So when I upload a new video like this, you will be able to get the notification in time. Thank you.